All right, so we're going to move on to 3.3. And 3.3 really dives into our derivatives now. We're really working into our derivative functions, and we're going to start learning, I guess you call them shortcuts, but they're shortcuts after we see the proofs. I'm not going to go over the proofs. I don't want to sit here and do a video on it when they're done very well in the book. So what I do recommend is, after we go over this video, open up the textbook 3.3, find the couple rules that we're going to look at, and look at the proofs. The proofs are based in limits, because derivative functions are based in limits, and it goes back to those limit laws that I showed you or gave you a worksheet or a sheet on. And they're pretty easy to see that they just follow along with the limits, so those rules are very similar to them, okay? So real quick, what we're gonna do is look at notation, just because I wanna point this out. It's always kind of confusing at first. So if you have a function f of x, its derivative function is represented by f prime of x, okay? So again, if you see prime, 1 prime means the first derivative, and then if I see f double prime of x, I'm kind of close there, this function is a derivative of that function. Notice I added a prime, so it's just kind of sequential. And you can go on from there. After 3, I think sometimes, I don't think I've ever seen 4, somebody put 4, but if you go past 3, so you can have like f triple prime of x. After that, we'll just put a 4 up there or 5, like that. But I've rarely ever seen anybody go past 3. 3, the third prime does have applications, so that's why I have seen that before, okay? Fourth primes and higher are usually used for theory. I haven't seen applications of those. Anyway, so going back to this, there is notation. In other words, there's kind of an operation notation that gets us from here to here. Okay, so if I take my original function f and I apply a specific operation notation, it'll get us to f prime of x, and that operation notation is d over dx, and I'll apply it to f of x, and that'll get me back, or get me to the f prime of x. So what is this d over dx? This is not d divided by dx. Technically it's delta, but we just use d just to stick with that and not have to write delta a lot, okay? And so what this is saying is I'm taking the d on top is saying I'm taking the derivative of this function, so d, derivative of the function f, and on bottom the derivative is being done with respect to the variable x. So the derivatives on the function f with respect to the variable defining this function as x, okay? Later on, we'll be looking at how can we take derivatives with different variables, respect to different variables. And yes, we can, and it's going to dictate certain things when we start working through it, this implicit differentiation idea, okay? So d by dx, this is also going to be done on y's, so if I have some y equals function, so just an equation, okay, and it's not defined by a functional name, I can apply it here. I write as d by dx of y. And get out, technically I can get out 2 things here, okay? One, I can get out y prime, I get an equation like that. So we do put a prime on the y if we want to. Or we can get out dy by dx, okay? And that's okay notation as long as we're using the variable y. So dy by dx are the same as y prime, okay? But notice the d by dx means I'm taking the derivative of y, okay? Pretty straightforward notation. But I always like to point that out because I don't think the book really kind of goes into details with the notation. It just kind of says, oh, these are the 2 different things. But I wanted to show that kind of, it's almost an operator that's moving things along when there's some notation that comes out of it, okay? So please make note of that. Okay? So let's look at these rules, okay? There's 1, 2, 3, 4, now there's 5 rules that we'll be going over, okay? And in that packet I gave you, the front page has those derivative properties on them, okay? So the first 4 are going to be the top 4 up here, okay? So these 4 up here, okay? And the one other one we're going to look at, I'm going to mention, is the e to the x, but we'll get to that at the end, okay? So the derivative, or the actual proofs of these are in the book, so I would recommend that. So I'm going to erase this notation over here and write these over here. That way I have the other side to work on, okay? All right. So we have our constant rule. Okay. It says the derivative with respect to x of any constant, meaning any number, numerical value, c, we'll call it c for constant, is automatically equal to 0, no matter what. Okay? And you can actually even do this graphically if you think about it. If I graph a constant, meaning I graph in a horizontal line, the rate of change of that, it's not changing. It's staying 0 because there's no y value change. Okay? So the rate of change of that is 0. That's a pretty easy one. Okay? The next one on here, make sure I'm going to do the order right. The book goes on to power rule. I wish it would do constant multiplier, but that's okay. Power rule next. And this is probably one of the most used rules. God, that's an awful R. Look at that R. Ugh. Do a better R than that. There we go. And the power rule is probably one of the most used rules we use, like singular rule. The most used rule later on that we'll learn is the chain rule. That's like your big time rule that allows for a lot of things down the road. But like singular rule on a small part is the power rule. So what the power rule states is this: if I take the derivative with respect to x of x to some power n, okay, so some power n. We ignore 0 here just because we can't deal with that. I mean, if it was x to the 0, it's already technically 1. It's a constant, so we ignore that. Okay. I think it's the only really kind of thing there. Negatives are fine. Negatives work great here. But this works out to be taking the power, whatever the power is, the power comes out for the derivative function. It comes out as a multiplier out front. So n comes out as a multiplier, n. My base for the variable x is still there, and I get a new power where I subtract 1 from the number up top. So I end up with n minus 1 up there. Okay? So we see when we take the derivative of a variable to a power, the power comes down as a multiplier, and I subtract 1 from the original. Okay? That's it. Okay? Next one. Again, I'm just going to write these up and we'll go over these for a second. So the next one up here is the constant multiplier. A pretty straightforward rule. The derivative with respect to x of some constant times some function. This function can be complex or non-complex. But basically, when I take the derivative of a constant times a function, the constant can come out front, and then I can take the derivative of just the function itself and work from there. In other words, a constant multiplier carries. Okay, we'll see this rule in action. Pretty straightforward. Okay. And the last rule that I have on there, yeah, we'll just do this. We'll wait on the e dx. Is the sum of difference form, the difference rule. Okay, a pretty straightforward rule. The derivative with respect to x of whether I'm adding or subtracting f of x plus or minus g of x, meaning I'm adding or subtracting two functions, whether they're complex or not. Okay, remember, a plus or minus just means plus or minus. I mean, just either way, it doesn't matter. So that holds the sum of difference. But we can break up the derivative over the sum of difference and say this is equal to the derivative with respect to x of f of x plus or minus the derivative with respect to x of g of x. In other words, we can break up the derivative function over a sum and difference and take each part of the sum and difference and do the derivatives on those. Okay, and again, all these rules are based in limits. So they follow those limit laws and limit rules. So if you look in the book goes through the proofs over the limits, and they're pretty easy to see. I mean, basically, if you think about it, I'm writing out limits, and then there's a sum here. So I throw the limit on top, break it apart, pull it apart, put it back together. It's not too hard to see in the book. It looks, especially like this one, it looks complex, but really if you follow along, it's a pretty straightforward proof. Okay? So, you want to try some? Let's try some, okay? We'll just jump into it, Okay? I'm not gonna make this video very long. I think these are pretty straightforward rules. They take a second to work with, but they're not too difficult to see. Let's just take our good old favorite quadratics. I'm going to jump into doing a full example, okay? So I have the derivative function f of x equals x squared plus 5x plus 10. Take a second, pause, and see what you get out of it, okay? So take a couple, just pause it real quick, see what you can get out, what the derivative function might be using these rules, and then we'll come back to it. All right, so if I look at this is a sum. So if I look at this function, I see a sum. That's kind of break down the function to figure out what is going on. So if I want to take the derivative of this, so if I want to take the derivative with respect to x of f of x, bracket, there we go. Take the derivative with respect to x of all of this, x squared plus 5x plus 10. I see I'm taking the derivative of a sum. Okay? So therefore I can use the sum rule and break up the derivative over each part of the sum. So if I break it up in here, d by dx of x squared plus d by dx 5x plus d by dx of 10. All right? And now we can look at each part. So break down each part in here. Okay? So if I look here, this is an x, that's a variable x to the second power. So if I look over here, that is going to be using our power rule. So our power rule states that I'm going to bring down my power as a multiplier. So my 2 is going to come down up front as a multiplier. It's going to be x to the 2 minus 1. So I subtract 1 from that original square up there. That's what the power rule states. The plus is just following from the rule. So now we move on to the derivative of 5 times x. All right, well, wait a minute. That 5 is that constant multiplier, okay? So that 5 being there can come down out front. And now we need to take the derivative of just x. Well, x is like the multiplier here, or our power rule here. X itself is just x to the first. So it's going to come down as 1 times x to the 1 minus 0. Okay? Too bad. And then I look at the last one. Well, I got the plus there. The plus just comes down because of the sum rule. And if I, that's bad. Let me rewrite that plus. There we go. And if I do that last one, derivative of 10. 10 is a constant. So right off the bat, I don't have to do anything. I say, that's just 0. I'm good because it's a constant. Okay? Now if we do some reducing real quick, this becomes 2x to the 2 minus 1, which is 1. I'm not going to put the 1 there. Plus, and then 1x to the 1 minus, oh, that should be 1 minus 1. I know, say something. 1 minus 1 there, okay? So 1 minus 1 there, my fault. So x to the 1 minus 1, that's x to the 0. X to the 0 is 1. 1 times 1 is 1. 1 times 5 is 5. Okay? So we could make a caveat, kind of side rule here off the power rule. Okay? The derivative with respect to x of x is 1. And I think that's pretty easy to see, okay, because I'm always going to subtract it. So that's kind of a cool little side rule there that you want to keep that in mind. Because a lot of times that kind of tricks you because you don't see the power and you're like, oh, wait a minute, what do I do with that? Well, it's just 1 itself. The x variable goes away. And so we end up with 2x plus 5. Okay? Let's quickly check. Limit as h goes to 0 of x plus f of x plus h, so x plus h squared plus 5 times x plus h plus 10 minus, make sure I'm on the board, yeah, okay. X squared minus 5x minus 10 all over h. So I get the limit as h goes to 0. That full is x squared plus 2xh plus h squared plus 5x plus 5h plus 10 minus x squared minus 5x minus 10 all over h. All right. So some reducing. Oh, let me get my bread out. Reduce, cancel, 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 cancel. Yeah, that looks like it's it. So I'm left with a limit as h goes to 0 of 2xh plus h squared plus 5h over h. And I think you can already see where that's coming out, right? So if I cancel out the bottom h with 1 from each of those, I'm left with limit as h goes to 0 of 2x plus h plus 5, which if that goes to 0, that's linear. I get 2x plus 2x plus 5. And I get what I want. Make note, just because we learn these rules does not mean we do not need to know how to do the limit, the h limit definition, okay? You gotta be able to know how to do that. Especially when we're dealing with later things down the road where we're working with things that don't have these rules. I mean, there'll be sometimes we might, where these rules just don't work. And so we have to know how to work through the h definition of the limit, okay, and be able to fully construct it, okay? But we can see it works out, okay? Not too bad, right? Let me give you, a couple to try. So I'm gonna write a couple up here, and I'll make you pause it, and then we'll go from there, okay? I mean, these rules are pretty quick and easy to deal with. It's just sometimes kind of thinking outside the box of how they work, okay? Let's see. Do g of x. H. There we go. Throw your root in there. Okay. So real quick, take a second, pause the video, and try to find the derivative of these functions using the 4 rules over here. Okay. So I'm going to move out of the way so you can pause it and look at the rules at the same time. Okay.